Alright guys, welcome back. We're going to start our second video for lesson number 2. This video is on continuity. And the first thing we're going to talk about is the 3 conditions that need to be met in order for a function to be continuous at a certain point. And then we're going to start showing you how to write stuff in proper notation. And let's go ahead and get started. So in order for a function to be continuous at a value of x equals c, right? There's 3 conditions that need to be met. Well, we've talked a lot in the last couple of videos about where a function is, the limit exists, right? So for a limit to exist, the left-hand side has to equal, right? The left-hand side has to equal the right-hand side. So it doesn't really matter what's going on over here, as long as we're approaching c, or x approaches c, that we're going in at the same value for y, which would be this number right here, this little guy right here. So let's just call that a. All right. So in this particular example, our limit would be equal to a. So not only does the limit exist, but it actually equals the value of a. F of c has to also exist, right? So what that means is that I have to value that's right here. So I could have a point right here and f of c exist, right? And so let's call this b. So in this particular example, f of c would now be equal to b. However, if you now look at this one, this is the most important one. This is the be all, do all one. In order for it to be continuous, these 2 values have to be equal to each other. So I actually have to get rid of this, and I'm going to put it right here. And now you can see that it is a continuous function. So now I've made this equal to a, and so now they're both equal to a. And so now I'm continuous. Let's just be honest about this. Continuity in layman's terms is you start on a graph and then you start tracing it. If you can trace it completely without picking up your pencil or your hand, then it's continuous over all the values that you're able to do that. We're going to talk about in this video types of discontinuity. The one that I was actually showing you, demonstrating for you guys here, is called removable discontinuity, where these 2 things do exist, but they're not equal to each other. We're going to get back into that a little bit later on. But for the purposes of this whole problem, in order for something to be continuous, literally you can draw whatever function you want. And so everything that I'm drawing right now is continuous at every value, because I can literally trace this entire thing and I do not have to pick up my pencil at all. All right, we're going to talk about types of discontinuity a little bit of time. Hopefully you guys can kind of already figure out the types of discontinuity. There are 4, but in calculus we really just talk about 3 of them. All right, so let's go ahead and do, okay, how do we prove it using calculus? So again, remember, these are our 3 conditions. The limit has to be equal, has to exist. The f of c value has to be exist or defined, and then they have to both be equal to each other. So if it's looking at this problem, it says, is f of x equals x squared plus 1 continuous at x equals 2? Now, you all know that this is a polynomial, right? The graph of this is a polynomial of x squared, and we've moved it up 1. So based on what I just said, you know that I can trace this thing from negative infinity to positive infinity and not have to pick up my pencil, right? Because it's a problem. So we want to know at x equals 2. Well, we already know the answer is yes. This could be any number, and the answer would be yes. But we want to show you how to write it in calculus. You want to prove it. You want to prove that it's continuous. So when I tell my students to say, I always tell them to write all 3 steps out. I mean, you have to, but I say in this order. You first want to say, is f of 2 defined? So I kind of wish that up here in the notes, I always do this one first, and then this one, and then this one at the end. So is my function defined at the value of c? And of course, this is the c, right? So 2 is c. So f of 2, that's going to be 2 squared plus 1, and that's going to be equal to 5. That just means that if I were to graph this function, that at 2, 5, I would have that value. The second thing is, does the limit as x approaches 2 of the function x squared plus 1 exist? And if so, what is the value? Well, in the previous lesson, we talked about limits algebraically and substitution and all that fun stuff. So you're going to substitute in here, right? This is a straightforward substitution, and then you're going to get that this is 5. All right? Now, you have to say, even though you see that these 2 things are equal to each other, you have to say that f of 2 is equal to. There's a lot of common sense that we know, but we have to make sure that you are stating for the reader, if you're taking an AP exam or for your teacher, you have to state that you know what the definition of continuity is. You know that that's what this is. That f of 2 has to equal the limit as x approaches to f of x. And again, make sure your notation is fantastic. Make sure you have your limits. Don't leave off your f of x. A lot of my students do that initially, and that's it. And then once you've done that, you can now say that f of x is continuous at x equals 2. If it ever asks you to justify your answer, you always want to make sure that you include the value that you have here, because when we're going to get to a couple more examples here, it may not be continuous at the value we're asking for, but it's continuous at other places. Okay, so that's a very straightforward, easy one for us to do. So let's go ahead and look at example number 2. Okay, so question number 2 says, is f of x equaling the absolute value of x over x continuous at x equals 1? In one of my previous videos, I've already talked to you guys about what this function looks like. And so we're going to really quickly graph it again, right? So very straightforward function, parent function we know here. And so it's asking us, is it continuous at x equals 1? So again, if you know what the graph looks like, you know that this is x equals 1. You know that it's continuous here. Again, this is where I need to say you need to stress what value we're looking at when we start writing these things out, because clearly in this particular example, it's not continuous at x equals 0, right? Because there's an asymptote there, right? There's an asymptote there. But we're going to look at where x is equal to 1. So again, practice makes perfect. We're going to do f of 1. We're going to plug in 1 to both of these. I'm going to save a little bit of time here. So the absolute value of 1 over 1 is just 1. So I know that that's defined. The second thing is I want to look at the limit as x approaches 1 of the absolute value of x over x. Students ask me, could we write f of x right here and the same thing right here? Absolutely, you can. But when you get to like other functions, you kind of want to specify what you're plugging into. So it's okay to put f of x here, but I always like to write down the function because I want to see what I'm plugging stuff into. Again, we're going to go back to substitution as we did over here, example number 2. So this is also going to be 1. And since now we have the fact that f of 1 is defined, and we have that the limit is also defined, and they're both equal to 1, right? Then we can say that f of x is continuous, and you can abbreviate continuous as CONT, at x equals 1. You want to make sure that you do stress this and you write that out, okay? You want to make sure you do that because it's not true for every value of x. But again, we only really care, in this entire problem, we only care about where x is equal to 1. All right, so let's look at a couple more examples and see what we can do with these, and then we're going to do a little bit of practice with this. So for question number 3, you see that we're given it as a piecewise function. So really the only difference between what we did at the very beginning in example number 2 and what we're doing now, that's supposed to be actually an open circle. Let me go ahead and do that for us, just because I want it to make it look pretty clear. So open circle, and now this is saying that when x is not equal to 0, then the function looks like this. And then this next part right here, this is saying, okay, well, x is equal to 0, then y must also equal to 0. So this is also a point of this. So it is defined at every place, so let's talk about that. So it's asking us, first of all, what is f of 0? Well, it's telling you right here that when x is equal to 0, you just substitute in. You plug in 0. It's just telling you plug in 0 right here, and so that's it. So that's going to give you a defined point. So we actually have a defined point. Then we look at the second question and says, okay, is the limit as x approaches 0 of the absolute value of x over x? Now, in this particular example, you can see that this is a not equals to and equals to, and we're going to do another similar question over here. I will tell you guys right now that if you have less than or greater than, then you're going to do the left-hand, right-hand limit thing. If you do not have a less than or greater than, then you never have to split the limit. You never have to go in step 2 and do a right-hand limit and a left-hand limit as we've been doing in the previous videos. So in this case, well, if we do substitute in, we do get 0 over 0, which we've talked about as an indeterminate problem, but you don't need to do anything algebraically because you know what this graph looks like, right? You're only doing algebraic stuff when you're not sure what the graph looks like. We clearly know that the left-hand limit, so I'm going to go ahead and actually draw this left in here. So the left-hand limit is going to be equal to -1, right? Because as I'm approaching this, I'm at -1. And then the right-hand limit is going to be equal to +1. So I know, and I'm still in step number 2, I know that my left-hand limit does not equal my right-hand limit. Now, I know I just said you don't have to write this out, and you don't have to because, again, you know what the graph looks like. I'm just doing this to show you guys that because these are not equal to each other, you can absolutely say, and this is the step that you could just jump right to, is that this overall limit does not exist. Now, if it does ask you to justify this, like why does the limit not exist, then you would have to write these 3 things out. So just look at the question. I don't ever imagine that we're going to ask you to do that, but that's really the idea of what's going on here. So since this limit does not exist, you do not even have to go to step number 3. So that's one thing I should have actually said at the very beginning, is that if this is a no, you're done. If it's not defined, you don't have to go through the steps. If the limit doesn't exist, see, I should have flip-flopped these. If it's not defined, then you're done. If the limit doesn't exist, you're done. You only have to go to this 3rd step. Even if these are not equal to each other, you still got to state that these are not equal, still for not continuous. But yeah, the point I'm trying to make here is, sorry, I'm being very wordy. The point I'm trying to make here is if one of these things fails, you immediately stop your problem. You don't have to worry about anything else. All right, so let's look at example number 4. I would encourage you maybe even to pause this and see what you can do with it based on what we did here. It is a little bit different than number 3, but I think you guys can definitely handle it. So let's go ahead and approach this question. So first of all, we're looking at, is this piecewise function? And you don't need to graph it. Again, notice that there is no less than or greater than sign here. So when I get to step 2, I'm just going to take the limit of this function right here. You always take the limit of the function where it's not equal to, and then what's equal to is going to be your f of c. Okay, so this is going to be your defined point. So let's look at that. So what is f of 3? Because we're asking you guys to find continuity at x equals 3. Well, it's telling you already right now it's 6, right? It's given that to us. So we know that step 1 is defined. We know that f of 3 is defined at 6. We now want to figure out what the limit as x approaches 3 of x squared over 9, or sorry, x squared minus 9 over x minus 3. Well, if we plug in 3 to the top, we get a 0. If we plug in 3 to the bottom, we also get 0. So we know from a previous video that this is an indeterminate limit. We don't know really right off the bat what this graph looks like. I mean, I know some of you guys pretty much know what this is, but since we don't know what it is, we have to continue on like we did in previous videos using algebra, and hopefully you guys know, and as BC students, I know you all know, that this top is a difference of 2 squares. Right? So you want to be able to do that. Again, ladies and gentlemen, please do not forget that you still need the limit notation. You have to do that. You've got to get really good at writing stuff in calculus. Right? It's really important that that I stress that with you guys. The x minus 3's cancel out, and so then you're left with the limit as x approaches 3 of x plus 3. And now we go back to our good old friend substitution. We plug in 3 here, and we're going to get that this limit is 6. Okay? So this limit is equal to 6. So after all that is said and done, I can now say that step 3, that f of 3 is equal to the limit as x approaches 3 of f of x. And yeah, you can also say is equal to 6. It doesn't really matter, but because you can say that, then you can now say that this is continuous, and I'm not going to write it out, but you would write out that therefore f of x is continuous at x equals 3. Okay? So hopefully that one is making sense. Hopefully that reiterated kind of what I was doing with example number 3. And like I said, you don't need to do a lot of these questions to really, truly, hopefully understand what I'm doing here. Okay, so now what happens when we do a piecewise function, right? Let's do a piecewise function. And let me actually get rid of this so we can... Yeah. All right, so for this one, when we have a less than, greater than thing. Now, right now, we're just looking at x is equal to -1. So we're really just looking at this little guy right here, and we're just taking this little piece right here. So I tell students, you know, if they're just asking for one value and they're giving you a lot of functions, just focus on where it says -1. I don't care about the 1 part right now, so I'm just looking at this. So I essentially could rewrite that. I'm not going to, but I could rewrite it and just look at these 2 functions, because this is telling me where x is greater than 1. Well, I'm looking at where x is -1, so I don't need this guy right here. So this is the left hand, right? It's going to be x is less than, so this is a left hand limit for this particular problem. And then this is going to be x is greater than -1. You can obviously rewrite it like x is greater than -1, and greater than is the right hand limit. So we have that. So we're going to do I'm going to do this all, hopefully all in green. So the first thing I got to do is I got to define it, right? So f of -1. And so the only time you look at the equals, right, is when you are defining it. So since it's up here, right, it's x is less than or equal to, I'm going to use this function right here. So this is where it's really important to show what we're actually plugging into. So it's 1 over x, which is 1 over -1. So we get -1. So when you've done that part that defined, you've also found, even though, and again, common sense, even though you've already found it, you still need to write it. You've already found the left-hand limit. And yes, I could have absolutely written 1 over x here, but since I've already plugged it in here, I don't feel like I need to. But you can if you want to. And I should be consistent really for these problems. So I'm gonna write up here what we're gonna do as what function we're gonna plug into. So it's -1 to the right, x is greater than -1, so we're gonna plug into this function right here. And we're gonna plug in -1, right? So we're gonna get -1 here. It's -1 minus 1 is -2. -2 divided by 2 is -1. So I'm actually gonna change the color up because it's getting a little green here for me. Still step number 2. So still step number 2. This one you do have to, so in example number 3, I told you guys you did not have to show the left and right hand limit because again, it's a not equals to and equals to. When you have an inequality piecewise function, you have to show these steps. You have to show these steps. So the limit as x approaches -1 of f of x is also equal to -1. Some teachers don't make students write this part out because when you write out step 3, I always have my students do it because I just want them to get used to, okay, if the left-hand limit is equal to the right-hand limit, then the overall limit exists. And the reason I have my students do it is because I want them to acknowledge that the overall limit's equal, and then you can now say that this overall limit is equal to this. So therefore, it is continuous at x equals -1. Right? So again, I'm at this moment in time, I'm thinking, oh my God, these examples. But I'm trying to show you guys diversity when it comes to these particular problems. So hopefully, the more I show this to you, the better you're getting at it, the better you're understanding it, and hopefully you can go back and do these problems like superstars. Okay, so let's go ahead and look at question number 5. Number 5, we're looking at where x is equal to 1. So x is equal to 1 here. This is x is greater than, so this is going to be our right-hand limit. And then we're just caring about this right here, this little guy, x is less than 1. This is our left-hand limit. So now that we've identified that, the first thing we're going to do is we're going to define, okay, is f of 1 defined? So again, we're going to look over this function, right, because it's greater than or equal to. And so we're going to do the square root of x, which is the square root of 1, which is 1. So f of 1 is equal to 1. Since we've now done this, we automatically have already found our right-hand limit because they're the same thing. So I can go and say the limit as x approaches 1 from the right, and I'm going to go ahead and write the square root of x, just to be consistent now, is equal to 1. So we've already found that. If we want to go and find the left-hand limit, and again, one of the things also I like about this is that I'm constantly doing notation. You can practice that. That does look like a 5, doesn't it? Sorry, I got distracted myself. It's -1. Just constantly doing these problems, I know may be overkill. I always like to explain a lot of my examples to my students, but I also want to just make sure that we're practicing notation, right? For all of this stuff. Look at all these problems here. We're practicing notation for this. So the limit is x approaches 1 from the left. Well, I'm going to use this function right here. I'm going to do x minus 1 over 2. I'm going to plug in 1 to our function. I get 0 over 2, which is equal to 0. So now you can say that this limit, let me write it up here. So the limit as x approaches 1 from the right of our function is equal to the limit of x approaches 1 from the left of our function. And students ask, can you write, square root of x here? And yes, you can, but in this moment of time, we just leave it like that. They're not equal to each other, right? So this is equal to 1, this is equal to 0. Therefore, not continuous at x equals 1. You don't have to go and talk about step number 3. Once we have got to something that's a big old no, then we're good. Okay? So those are very crazy long questions, but when you're doing FRQs, free response questions, you're going to be expected to show work like this. Okay? So let's see. Hopefully that makes sense to you. Now we're going to shift gears and talk about discontinuity and types of discontinuity. So on the next page, we have 3 examples of discontinuity. There are actually 4 of them. The oscillating one, we don't really get to too much. I don't really even see examples of that. Maybe they'll bring it back into curriculum. But so these are the three that we really focus on. Remember at the very beginning of this video, I told you guys that the best way to define continuity is to take our marker or a pen and we're starting to trace. We're tracing, and then when we get to here, we have, a problem. We fall into this hole, right? We can't just go, think about we're walking on a path and we get to a hole. We can't walk over the hole, right? We are going to fall into the hole. So at x equals -1, we have a discontinuity, right? Discontinuity. And so in this particular example, you can see that this is based on the graph. This is a hole in the graph at x equals -1. And what we call this is removable. Removable. And yes, you need to know these words, removable. I could have something defined as of right here. I could say f of -1 is 1. Okay, good. It's defined. My limit, as we talked about in previous videos, my limit is 0, right? My left and right hand limit 0. So they're not equal to each other. Therefore, it's not continuous. The only thing else I want to say about removable compared to the other two is that removable discontinuity, what makes this stand out is the limit as x approaches c of f of x will always exist. For the other two examples, it will never exist. So if you're looking at discontinuity and it tells you the limit is existing, then you know it's going to be removable without giving any other information, because it really is just a graph with a hole in it. And at a hole, the limit will still exist. And I've talked about this many times in our examples we've done. It doesn't matter what's happening specifically at the point for a limit to exist. It does matter what's happening at the point for continuity, but for limits, we're okay with that. So that's removable. And for this example right here, again, I'm tracing, and then I have to pick up my pencil to actually move to this part right here. So I have to, and I always tell students, like, you know, we're walking, and then we literally have to jump up or we have to jump down. So this is a jump discontinuity. This is always identified as a piecewise function. Okay, a piecewise function that is not connected. Okay, that's not connected. Again, it does not matter if they're both open. Clearly, they can't both be closed because then that will be a function. But if they're one open, one not, it doesn't matter. It's still defined, right? So if I look at this example right here, it's defined. And I could do the whole law of continuity, but we've already talked about that so much already today. That f of 1 is defined. It's equal to -2. The left-hand limit is -3. The right-hand limit is -2. Therefore, the limit doesn't exist, right? So this limit will not exist. The limit as x approaches 1 of f of x does not exist. Therefore, it's not continuous. So I don't care that it's defined or not defined. This is the whole part of that. And then the last example that we're going to look at is what's happening with our example like this. Well, at x equals 1, there's an asymptote. I think in lesson 1 we talked about, maybe it was the first video, I don't remember, infinity, right? So the left hand, first of all, it's not defined, right? It's not even defined. So f of c is not defined. And I should say undefined, right? Undefined. Sorry for my handwriting, that's horrible, but undefined. So it's not defined, and that's a good point to make about this one. And then, there's two ways to say this one, but we're just going to stick with infinite. All right, infinite. And I always tell students that infinite's the easier one to do for this. Asymptotic is the other way that you would define this. It would just be the IC. But infinite's the easiest way to do this because, our limits, usually our left and right hand limits, are going to infinity because there's an asymptote here. So these are our three types of discontinuities. We have a removable, we have jump, and we have infinite. Again, removable, the limit will always exist. Jump, the limit will never exist. And infinite, the limit will never exist. And f of c should probably not be defined as well. All right. So I think that's pretty straightforward for most people to do. If you look at example number 6, we have 2 more examples to go, and then I'm going to shut this video off. It says, at what points is the graph discontinuous? And then on what values is it continuous? So clearly, if it's discontinuous, then it's not continuous, right? So So let's look at this graph right here and see what's happening. And so where is it discontinuous? So you guys could probably take a second and pause this and write out where it's discontinuous and then what type of discontinuity is it, right? Okay, so let's do this. Again, if you pause it, great. So x equals -2 is our first one, right? X equals -2. I can't go on my graph right here and then just come right back down, right? There's an asymptote that's understood to be up here. So this is that. And then what is the discontinuity? It is infinite, right? And because it's going to infinity, right? The limits are going all the way to infinity. So we have that. Then let's look at x is equal to 0, right? X is equal to 0, and that is because we have a jump. And again, it's because it's a piecewise function, right? There's a jump here. And then the last one is at x equals 2, and that is removable. So these are really easy pictures for you guys to see. Again, if this dot had been gone, then it still would be removable. So it can be defined. It doesn't have to be defined. I know there's a little dot right here. I just think they put it on there just to show you that, yeah, you could have a dot on the asymptote at some value, but it's still the limit doesn't exist because it's positive infinity, positive infinity. I know that some people in my students like, okay, what's going on right here with these sharp corners? They are continuous. That's another conversation we're going to have in another video about what is going on right here. It's continuous because, based on my very basic definition of it, I can go and graph, and I can go and follow this thing, this function, and not have to lift up my my pen, right? And some people didn't even think about, what's going on with these sharp corners. That will come back into play when we talk about differentiability. Okay. So it says, on what intervals is the graph continuous? On the closed interval from -5 to 5. Well, -5. So basically it's just everything but these two values, right? It's -5 to 5. Now, this is where students start yelling and be like, why are you not putting brackets here and here? In calculus, it doesn't really matter. I know that really, in unions, like why isn't there union? You can put unions in there. You can do brackets all you want. It does not matter. So I just tell students that just parentheses is always the best. You definitely want to make sure you do parentheses, right? You don't want to just leave it like that because that could be a vector. It could be a transformation. And we do get into that in BC calculus. So it's really important that you are doing this. And don't try to be cute with, and I've seen this before where kids do something like this and I'm like, what is that? What is that? Is that a parentheses or a vector or some caret thing? And I will tell you that they're not going to give you the benefit of doubt. The readers are not going to give you the benefit of doubt. If they can't read it, then they're not going to give you the points for it. So you just want to be really careful with that. Okay, the last example we're going to do, and yeah, so again, if you're my student, there's a lot of theorems and stuff like this that you see. We did this in lesson number 1. This was actually lesson number 1. This is video number 3 about the composition stuff. So that was the really crazy stuff that we did. So it's put there just because now we're talking about composition limit theory again. I don't really know why it's there, but it doesn't matter. Last example, because I know we're probably tired here. Is this function continuous for all real numbers? All right. So again, we don't know what the graph looks like, but in this particular example, you can manipulate. It's all about manipulation. So if you look at this and say, okay, well, this is going to be the square root of x plus 3 squared. And then I can say, oh, okay, that's just x plus 3, right? And so f of x is just y. So this is the line. This is the line x plus 3. So the slope is 1, and we're here at 3, right? 1, 2. And so our slope is like this. I can't hit that point, so let's make it much, much bigger. There's my huge point. So it's the line y equals x plus 3. So we clearly know that the function is continuous at all real values. So yeah, it's continuous for all real values. Okay, so that is the examples for continuity. This video went a little bit longer than I thought, but it's okay. I just want to go through as much as I can, as thoroughly as I can for you guys. So let's get back to our next video. We're going to talk about IVT. So hopefully you guys are now masters of continuity. So I will see you guys in the next video.